All right, let's talk about something that sounds like it's straight out of science fiction: the mathematical blueprint for building quantum intelligence. If you've ever been curious about what it actually takes to get your hands dirty with quantum machine learning, well, you've come to the right place. Let's get into it.
So, what is this blueprint? I mean, really, it's not some fuzzy, abstract idea. Nope. It's a very specific set of mathematical tools. Think of it as the DNA, the fundamental code that lets us write the rules for a whole new kind of AI.
And the whole idea for this comes from a really clear 1 month roadmap. Don't think of it like some dusty old textbook. It's more like a workout plan, a 4 week sprint to build the essential mathematical muscles you need for this stuff.
And here it is, the whole journey laid out. It's basically built on three core pillars. Weeks 1 and 2 are all about mastering the language of the quantum world. Then, week 3 is about tackling the logic of uncertainty. And we finish it all off in week 4 by building the learning engine. So let's break down that first pillar. Okay, pillar number 1, the language. This makes perfect sense, right? Before we can get a quantum computer to do anything cool, we have to know how to speak to it. And that language, the absolute foundation of quantum mechanics, is linear algebra. Linear algebra gives us everything, the whole grammar, all the vocabulary we need to describe these quantum systems. It's how we take all the weird, mind-bending rules of the quantum realm and translate them into a structure we can actually work with.
And you know what's kind of wild? The most basic word in this entire language is just a vector, a simple list of numbers, just like this one. It can be a point in space or a piece of data, or, and this is the key for us, it can represent the state of a quantum bit, a qubit.
So if you think of vectors as the nouns, then matrices, well, matrices are the verbs. They're the action words. A matrix is just a grid of numbers that tells us how to transform a vector, how to rotate it or stretch it. And in the quantum world, this is exactly how we model what quantum gates do to our qubits.
But here's the catch. You can't just use any old matrix. Week 2 of this roadmap introduces us to these special types, like unitary and Hermitian matrices. And here's why that matters. A normal matrix can do whatever it wants to a vector. But these special quantum ones play by the rules. They're like precision tools that make sure all our quantum math doesn't, break the laws of physics.
So that's how we handle one qubit. But a real quantum computer has lots of them, right? So how do we describe them all working together? That's where this thing called the tensor product comes in. It's the mathematical trick for weaving all those individual qubit states into one big, powerful system. Without it, we're stuck in the minor leagues. Okay, so we've got the language down. But let's be honest, the quantum world is weird. It's built on chance. And that brings us to our second pillar, the uncertainty. This is all about probability theory. See, a qubit isn't just a 0 or a 1 until you look at it. It kind of exists as a blend of both states at the same time, a superposition. Probability theory gives us the strict rules we need to manage all that weirdness and figure out the odds of what we'll see when we finally take a peek. And the way we start to wrangle all this uncertainty is with something we all get, a simple coin toss. The roadmap starts us off with the basics, just figuring out all the possible outcomes and the chances of one specific thing happening. It's simple, but it's the bedrock. From there, we build up to something way more powerful, conditional probability. That's just a fancy way of asking, okay, if this thing happened, what are the chances that that thing will happen next? And this is absolutely critical, because in a quantum algorithm, measuring one qubit can totally change the odds for another one. You have to understand these connections. Okay, we have the language to describe the system, we have the rules to handle its uncertainty, but how does it actually learn anything? For that, we need an engine, and that's our third and final pillar, calculus and optimization. This is it. This is where the machine learning part of quantum machine learning really kicks in. Calculus gives us the tools to measure change, and optimization uses those tools to get better and better, step by step, finding the best possible answer to whatever problem we give it. And the process itself is actually this beautiful, simple loop. First, you measure how well your model is doing. Is it good? Is it bad? Then you use a bit of calculus to find the exact direction to go to make it better. And third, you just take a tiny step in that direction. You update your model, and you do it all over again, getting a little smarter with every single cycle. So we have all the pieces on the table. We've got the language, the rules for uncertainty, and the learning engine. Now for the finale. Let's put all the concepts from our 4-week blueprint together and see what we've actually built. First, we use the language. Linear algebra lets us define our basic building blocks, these fundamental states of 0 and 1. Then we bring in probability. This lets us describe the qubit not as just a 0 or a 1, but as a combination of the two, with certain odds for each. And finally, we switch on the engine. In a real QML algorithm, we use calculus and optimization to tune that qubit state, to nudge it, guiding it step by step closer to the answer we're looking for. And all of that, the vectors, the probabilities, the optimization, all of it comes together to let us write this one single elegant expression. This is it. This is the complete mathematical description of a single qubit. It's the result of everything we just did. And that's the real punchline. After just 1 month, this roadmap takes you from 0 to here, to having the fundamental power to describe in perfect mathematical detail a little piece of the quantum universe. That is an incredibly powerful place to be. Which, of course, leads to the big question. The blueprint isn't a secret anymore. It's out there, it's clear, it's accessible. The real question now is, who's going to pick up these tools and build the future with them? What will you build?